Hey guys, so this video is going to get more into the types of situations in which you would use parametric equations. So pause and read it and then continue. Basically, parametric equations can model projectile motion of an object. So we're given an x equation that's going to represent the horizontal motion of the object and a y equation that's going to represent the vertical motion of the object. There's a lot of stuff in here. First off, note that you'll always be given the x and y like base equations, and then you just have to fill in all the extra stuff. So that thing that has v sub 0, that is just the initial velocity. And if you want to go ahead and make these notes as well, that would be super helpful. Cosine of theta, so theta is going to be the angle that the object was hit at. So if I come to this next slide, you can see we're tossing a pumpkin here, and it shows you theta is 45 degrees. So theta is just going to be whatever angle it's hit from. T is obviously still going to be time. H in the y equation is going to represent the height that the object was either hit from, thrown from, whatever is used there. And then you've just got that initial velocity and angle again in the v sub 0 and sine theta. And then the minus 16t squared, the t is still going to represent time. That is actually just going to be like a constant that's used for gravity. But that is not something that we need to be worried about now. You will be told the equation in which to use. So basically, to model these situations, you're going to be given this base x and y equation to use, and you just have to fill in the information for it, which is what we're about to do. So again, go ahead and pause to read the problem, and then unpause whenever you are ready to start solving it. So in part A, we want to write a set of parametric equations to represent the motion of this pumpkin. So we're going to start with the x equation. So x equals, and the first thing we need is the initial velocity, and it gives us the initial speed here is 125, and then times cosine theta. So cosine theta is 45 degrees, and then times t. And then our y equation is going to be the height that the pumpkin was catapulted from, which is that 25 feet. So 25 plus the initial velocity, which again is the 125. This time it's going to be sine theta. So 125 times the sine of 45, and then all of that times t, and then minus 16t squared. So that gives us our initial x and y equation, and then that's what we're going to use in part B to find how far the pumpkin travels. Okay, so to find how far the pumpkin traveled, how far means that you want to see the horizontal distance that it traveled. So that is going to be using the x equation. But we can't start with just the x equation, because to know the horizontal distance that the pumpkin traveled, first we need to know how long was the pumpkin in the air, because that's going to give us our t in the x equation. So this is going to seem a little bit weird, but to figure out how long the pumpkin was in the air, we're going to look at this y equation as if it was in rectangular form. So basically, we just need to know when that y equation, like when does the pumpkin hit the ground? So we need to know when y equals 0. So to do that, you're going to want to graph the y equation in regular function mode on your calculator, or in my situation, I did it on Desmos on the computer. And so this is the parabola that was created whenever I graphed it. I just used an x in place of t. It's the same thing as if I was using t. It's just in function mode instead of parametric, since I'm only using one equation. So then I came over here to settings in Desmos, and I made sure that I put it in degree mode, because for the sine of 45, that's the sine of 45 degrees. And then I noticed that I couldn't see the top of the parabola, so I just changed that y-axis so that the maximum was a lot higher. I set it at 150, and then whenever I come back over here, the actual maximum height the pumpkin reached was 147. I think it's super cool in Desmos that I can just click that. And with that being said, I can also come down here and just click that point and get my 0. So I know that the 0 is at 5.794, and that means that the pumpkin was in the air for 5.794 seconds. And so I'm going to take that back, and I'm going to use that for my time in my x equation to see the horizontal distance that the pumpkin traveled. So I want to start by saying I don't know why Desmos is such poor quality in these screen recordings. I'm really sorry about that. Obviously, if you're typing in the equations and everything, you can see it a little bit better though. But anyway, what we just found out was that the pumpkin was in the air for 5.794 seconds, and we want to know the horizontal distance that it traveled. So we're going to take that time of 5.794 and plug that in for t in the x equation. So now x equals 125 cosine of 45 times 5.794. And so obviously you can just type that in a calculator, make sure that you're in degree mode if you do so, but I'm going to come back over to the internet and just type it. The first thing I'm going to do on my calculator is just type in cosine of 45 degrees, because I want to make sure that it's in degree mode. And then I'm going to take that and multiply it by the 125, and then again by the 5.794 for the time. And you should get that the pumpkin traveled 512.12 feet. And so I'm going to come back over here. Okay, I just want to do one more problem here. And so in this one, we have a water skier jumping off of a ramp, and we're trying to model the motion of his jump. So the first thing in number 33 that it wants us to do is just write a set of parametric equations for the jump. So we're going to start with that. So we first have our x equation, which equals the initial velocity, and he jumped at a speed of 17.9 meters per second. So we're going to put in that 17.9 times the cosine of the angle that he jumped from, and it gives that to us here, that 14.3 degrees, and then times t, which is time. And then our y equation is going to be the height that he jumped from, which is the 1.71 meters, plus his initial velocity of 17.9 meters per second, times the sine of that angle, which was the 14.3, all of this times the time, and then minus 16t squared. Minus 9.8 t squared. And I was about to make a note of that too. Notice that in this one we're using 9.8. That's just because it's meters per second. Whenever you're using feet per second, you would use the 16t squared for gravity. Whenever we're using meters per second, we're going to use 9.8. That's just the metric constant that you're going to use for gravity. So that gives us our parametric equations for this problem. So in number 34, it wants to know how many seconds is the water skier in the air. So if he is no longer in the air, that indicates he has hit the water, which would make his height 0. So this is the situation where you want to set this y equation equal to 0. So I went ahead and put it in Desmos for us. Here's our equation. And I just need to find where y equals 0, which is right here at 0.70. So for how long is the water skier in the air? He's in the air for about 0.7 seconds. So for number 35, that is talking about how far from the ramp does the water skier land, and so that's talking again about the horizontal distance from the ramp that he goes out. So since it's horizontal, we're going to be using that x equation. So we're going to have x equals 17.9 cosine of 14.3 and then times time, and the time that we found using our y equation was 0.7. And so then I'm going to come back to my calculator and I'm going to put in first cosine of 14.3 degrees like that so that you make sure it's in degree mode, or just type it in your calculator and you should be fine. And then we need times 17.9 and times 0.7 for my time, and you should get 12.14. So the distance that this water skier traveled was 12.14, and it's in meters. And so that would be the answer to number 35. So that's really all for projectile motion. Remember that you will be given these x and y equations, so you don't have to memorize them. That's just the basic equations that you're going to put that information from the problem into, like the angle, the height, the velocity, and all of that good stuff. Also, remember you'll typically be using the negative 16t squared for gravity whenever you're given it in feet per second. Sometimes you may also use the negative 9.8 t squared for our gravity whenever you're given the information in meters or in metric units. And so that's about it. This may seem intimidating right now, but essentially you'll just need to practice some of the problems and you should be able to get it pretty quickly over time. And so that is all. I hope you guys have a great day. And I'm sorry that I spelled initial wrong. Let me just